My team, where we work, we're a data factory, and my team's the shipping department. Okay, close enough. So, but this is not about what we do in my team so much as a problem that I encountered helping somebody else at Hale. And this problem is a different kind of computing than what I was used to, where there's real world events where people will have proposals, projects, they might be grant applications, they could even be papers, they could be plans for gas terminals, oil field preparation, all sorts of things where there's some idea of a project or proposal that has to go through an approval process. And then depending on what kind of approval process that is it security or engineering safety or environmental, then the people who had the proposal have to go back and edit it and iterate for a while before it can finally be approved and get done. In a simple case, this would be classic peer review for papers. And so organizations that do any kind of approval at scale will have some system that's recording the events of the proposals, whether it's a paper for a journal or a plan for a liquid gas terminal. And that proposal will go through an approval process that where it gets reviewed, it will go through iterations. At some point they say, you've got to like just seriously revise this, not a few things here, but come up with a whole new version, not just a little change, but a big change. And the lifetime of getting that project off the ground before anybody does anything could be kind of like a GitHub repo, where all you have is forks and not merges. So you start with the main branch, and then you fork it, and you do something, and oh, maybe you back up and fork it again. And at some point, one of those forks, hopefully, survives, and the project moves forward. Well, the people that are involved in managing the people who are doing the compliance and approval process might want to get business intelligence about how efficient, how are we doing? They're going to want to look at those records. And so somewhere in the database, there will be records, but one proposal won't be a single record. It'll be a whole bunch of events in the database. There'll be a kind of log, but not like a server log that some of you might be used to, where you've got hundreds of events per second, but a log where one event could mean an actual meeting of people, or the event was somebody reviewed some documentation and returned a result. So I simplified what we were encountering there to like, here are some typical types of events. You know, there's an initial event, which is draft, but another type of initial event would be revise. That's where, oh, you really need to make that would be like you're doing a fork, and maybe going back a ways and then starting the fork. There's the review and update. That's just like the iterative process. You've got the terminal events, approve, reject, and withdraw. And then there's the revise one is not only an initial event, but conceptually it terminates the previous one, because it's like we're not following the version 1 anymore. We're now following version 1.1 of some proposal. And you know, at any given moment, you need to know like which version of the proposal is in play and being reviewed for whatever kind of compliance matters. Okay, so here's an example of an ideal event log where the ID will be the proposal, the project, the paper, whatever it is, the thing that you're concerned about. And we see that there's a date, and then there's the person, I'm calling the planner, and the reviewer. You know, so that's going to be the back and forth. There's going to be like, and what happened. And you see I've color-coded this, so it makes it really easy to follow what's going on here. So on January 1st, Marcus drafts proposal 1 and goes over to Finn for review. Finn gives his comments, Marcus does an update, approved. This is such a simple event, I view this as very much a corner case. A thing that would probably be fairly rare. That, a simple revision and you're done, and you didn't have to go back and do any major revisions. More common would be, and here color coded in blue, it started off as ID number 2, but then when Diego did the review, Elena had to revise it, and just we're doing a rewrite. So going from 2 to 4 is this rewrite of the proposal. But that one, after a little bit of iteration, got done. Diego approves it, out the door. And then number 3 is more like what you're really going to really see happen. So Jasper came up with proposal number 3, Ari reviews it, Jasper revises it, Ari goes, no, it's just too broken. So Jasper revises in a different direction, Ari, Jasper withdraws. And then Jasper comes up with a third revision. And notice that the parent IDs are all the same. So these are like forks from that same starting point. And that one finally did get through. And that's a little bit torturous. Usually there might just be a single dead end. Here we've got 2 dead ends before we got to a conclusion. This is giving sort of the flavor of the kinds of records that are stored in these enterprise databases where a single transaction event in the record is a human thing. People in real life either met or looked at pieces of paper and did something in a very official way. And that's why I'm doing dates rather than timestamps of hours, minutes, and seconds. Okay, so that's an ideal event log. This is what it's going to look like instead. Everything's sorted by date. It's not color-coded. It's not grouped. You can't make heads or tails of it like you could, with me explaining it to you. You could follow along what's going on here. And there's going to be many, many, many of these with the real event log. And so you can't do it by hand. And because we have these relationships between these IDs, this is something that's going to break Excel. And it's also going to break even the relational model. Anytime that you've got some kind of hierarchy that's forming trees, which is what we're having here, then the relational model starts to break. Even the standard employee database, where you have managers managing managers who are managing employees, is something where asking a straightforward question like, what are all the people that directly or indirectly report to some mid-level manager, does not exist in closed form in SQL unless you assume a maximum possible depth. And if you do assume some maximum possible depth and do it, you're going to get a horrible query. So we're outside the realm where sort of the normal way of applying just Pandas tables or relational database tables is going to help us. We're in trouble. And DAX is not going to come to save us for people in Power BI. We need to reach some tools. The interesting thing is, this isn't necessarily a lot of data. It's not a server log. It's not going to blow up your computer, your laptop, your Raspberry Pi. It's just more than you can fit in your head. And because it's connections, it breaks Excel. So let's see what we can do with this. So Python has a built-in library called NetworkX. And this is a library for working with what are called graphs. And I'm trying to minimize theory here, but a graph in this case is not a plot like you do for data. A graph is circles connected by lines. That's a graph. And if the lines are arrows, that's called a directed graph. If you can never start at some point and follow arrows and get back to where you started, well, if you can, that's called a cycle. But if it's not possible anywhere to start at some point and traverse the arrows and get back to where you started, that would be called a directed acyclic graph. Every hierarchy and every tree is a directed acyclic graph. The commits in GitHub form a directed acyclic graph. The difference between Git commits and a hierarchy is that merging is an allowed event. Whereas in this case, we're not allowing merging between proposals, although real world, some level of informal merging is happening, where somebody will take some ideas from something and just copy paste it in. But we're not going to worry about that, because we're just trying to track like how efficient are we at cutting the red tape and getting through an approvals process so that the gas terminal gets built, people get paid, and money gets made, type of thing. So this is just some boilerplate in the notebook starting up. I'm just sort of loading that data. So here's that same data. And the first thing I do is I'm just going to wrangle it using a standard data class. So these are the same columns that I showed you before. And then I'm just doing a little bit of magic to coerce things to the right type. You don't really have to worry about that. I did do one like really clever thing with the str for this example, is that when you print one of these events, it will give you the project number followed by the last 2 digits of the date. And that just makes it easy to read for this toy example. And so these are examples of what those look like. Okay, so now I can start grouping the events, and then I can apply some business logic to it. I've got my idea of terminating events. I can start identifying events as forming sets. All the events that have the same ID. That's the first bit of logic. All the events that have the same ID, conceptually, we'll be able to collapse those into a single object, which for this purpose I'm calling a chain. But at times I also call it a project. So that's not such a complicated thing. We start getting events that look like this. Now, none of this so far is doing any network stuff. We're still doing the first pass data wrangling, where I'm just reducing the complexity of it by identifying, here's a group of events. They're in order. They all have the same ID. We're going to say that's a chain. Going to collapse it to a single dot, because topologically, we're only connecting like the end of one chain to the beginning of other chains. So I can do that simplification. So here's like data class where I'm defining the chain. I've got the idea of the ID. All of the events in the chain will have the same ID. There may or may not be a parent ID. What does it mean if there's no parent ID? Well, that means that this was like the initial version of some proposal. I've got the idea of an end date and an end event. So if you, in a chain, if there's an event that is withdrawn or approved or rejected, that would be a terminal event. We're going to note that here, because that'll be useful for our business intelligence. We want to know how many days or weeks or months it took to get from a proposal to a final conclusion about this project can now actually start doing stuff. Until then, it's all going to be paperwork and compliance. So when is the project, like, at least at a logical level, shovel ready? So I organize, I start assembling the chains. Nothing all that special about it, just some for loops. And I do have some clever ways that I'm defining here another clever stir just to make it easy to understand what's going on. So now, where I had the date on an event in a chain, I'm going to have the parent ID, or a space. I don't have a parent ID, and then dashes, the ID of this chain, then when did it start, when did it end. And by making that be the printout of any particular chain, that makes it easy to see what's going on and just sort of reason about this. So these are what the chains look like. So we see, here's our first three chains. You know, they were the ID 1, 2, and 3. So, and they've got gaps there because they did not have parents. But then we've got these others down here that did have parents. We saw that 2 eventually reaches an end with the revise event, which is its sort of terminal event, gave rise to 4, which got proved. The proposal that started out as 3 got rejected, got withdrawn, then approved. So just forming the chains, we're starting to make sense of it. But one of these is not telling the whole story. Like the 3 down here at the bottom, no one of them tells the story. To really tell the story of these bottom 3, I have to also include that one there. So I need, even after I've collapsed as much as I could with that kind of aggregation to form events in the event chains, I still need to say that 4 of those equals one conceptual thing. One project was 4 of these. Now, for the really simple ones, it was just 1, or it was just 2. But you don't want to have to wade through this. You don't want to have to stare at this. This could be hundreds or thousands. Still, way easy data for your laptop to manage. But if you try to start analyzing this by hand at scale, you're going to make mistakes and start losing your will to live. So we know that there's linkages between these things, and we're trying to extract information from those linkages. So this is where I'm saying graph. Remember, graphing and plotting are 2 different things. It's kind of like football. When I say football, am I talking about a game played with this pointy ball, or am I talking about a game played with a spherical ball? It's ambiguous. Graph is like that. So I reserve the word plot for its data, and you're getting like scatter or bars or 3D, and I reserve the word graph because there's no other use for it, for no other term for it, for circles connected by lines on a whiteboard. That's a graph. Just like the rest of the world doesn't say soccer. You know, most of the world just says football. And soccer is not a standard term. We say graph. Okay, so I use NetworkX, and so I import. It says NX. You create an empty graph. Now, a graph is really just a kind of dictionary. And so under the hood, this is all just dictionaries. If you have very, very large graphs, then there would be matrices and sparse matrices representing the connections between edges. But NetworkX is not for data at that scale, but it does apply the standard algorithm. So we're using this rather than writing our own, so we don't waste a lot of time writing code and introducing bugs with with the code that we'd be writing to try to implement the basic graph algorithms. So anything, what can you store in a graph? It's anything that you can store as a key in a dictionary or as an element of a set can be a member of a graph, because ultimately they're just going to use dictionary keys to tie all this together. So your objects have to be hashable. They can be integers, they can be strings. In my case, there are these chains, but I'm using this string as the input to the hash. I think that's what I can check. No, I'm actually just using the ID. That works too. Anything that was like unique, so no 2 objects had the same hash, would have worked. Although, actually, even if you have a collision, it still would have worked. But it has to be hashable objects, so you have to define a hash function. Okay, so let's take a look at what we've got. I load it up, and this is where my clever stir now helps me. You know, rather than just seeing numbers and going, what was going on there? Now the picture emerges. We see that number 1 was like super simple, nothing much to say about that. Number 2 just had 1 major revision and then eventually done. And then number 3 did 2 dead ends to the top and the bottom and eventually got down to here. And So that just immediately falls out from just loading the data into a graph object. And then it's like, well, I'm gaining insight just by looking at that, but the whole point of this exercise is so that the human doesn't have to look at this, because there's going to be way too many of these. We need automation to sort through a non-visualized version of this and pick out these constellations for us and go constellation 1, constellation 2. So we started with individual events. Events became chains. Those chains are forming these constellations, which, okay, another bit of theory, are called subgraphs. This graph decomposes into these subgraphs. A subgraph is a subset of a graph that is not connected to any other part of the graph. So they form these disjoint sets. Okay, so I start analyzing the graph to say, well, what are all the nodes? So how am I going to process this further? Well, I know that some of these nodes are parents, and some are children. And in a more typical case, which I've simplified out, there could be some along this line here. There could be nodes that are both parents and children. And I simplified that out for this synthetic example, but real world we would have that. And so we can do some logic where we say, well, any node that has no parents is going to be some kind of root node. And any node that has no children will be some kind of leaf node. And you will have some special nodes like this one, which you can think of as islands. It's both a root and a leaf. And because I can now start assembling those using sets, we've got the standard Python set logic to reason about this. And away we go. So I say, well, just take a set of all the nodes. Okay, and this is them up there. And then I could say, okay, first graph algorithm I get, show me all the successors. Show me all the linkages in a Pythonic data structure. So here we go. It's a dictionary of nodes where so the keys are nodes and the values are lists of nodes. Those are going to be the linkages. And so every node that has children will appear in here. Nodes that don't have children will not appear in there. So the island does not appear in there. And simply analyzing this is sufficient to start working out what these anchor points will be. So I say, well, parents are going to be, everything that's a key in this dictionary is a parent. Everything that's value in that dictionary is a child. And so I can start, so I created this children's set. That's how I did that. I just moved over it. I can get the parents that were computed, get the children that were computed. I then have this little bit of business logic that said, well, the roots are either my islands or the parents that are not children. The set of all nodes that are parents that are not themselves children must be roots. And the set of all children that are not themselves parents must be leaves. And there we go. These will be my sort of anchor points to now traverse the graph once we've decomposed it into subgraphs. So there's my islands. And now it starts going fast. So this is just my display format. I say, okay, starting in all of the roots, but also the islands, which actually I think that might be redundant. I'm going to check to see if there's a path. So I'm starting with all the roots and all the children. I say, is there a path between this root and this leaf? If there's a path, hey, NetworkX, give me that path. Okay, and then it gets that path. And then I'm just going to print out all the elements in that path in the order of the path. That's going to be giving me that history. And if I didn't have a path, then that meant I had an island just printed out. And look at that. So here's the result. It is the correct result. We can read, like looking down, we see there's one by itself. There's sort of two forming these two lines. 3 was got broken down into 3 different paths. So if I organize this into a table, where NetworkX was so first I wrangled, then I did some network processing, then I get a table. At this point, the business intelligence I want to extract is going to be a fairly straightforward aggregation of this. I can now take, say, all of these that begin with 3 and group them together to say what I really want. So going back to over here. So what did I want in my event log is something like this. This is the kind of business intelligence I'm after. But different people may want different things, and you can imagine this as being the center of some kind of fact table where there's like many-to-many relationship between these things and the people. I didn't process the people, but those would go in a separate lookup table that I could then have a join table connecting. It just depends on like what is the business intelligence you're after. You know, what are the insight products you're trying to generate? But I can't get to here unless by using automation, I can get to here. And I'm not showing it, I haven't done it, but it should be fairly straightforward using Python, and at this point I'm beyond using graphs. That going from here to there is a pretty mechanical process. And that's the idea. When you've got data where some significant fraction of your business intelligence is the linkages between rows. When it's connecting rows across tables by foreign keys, that's a solved problem. But when you have rows in the same table that are connected to each other, that's when you get in trouble. Pandas breaks down, Excel breaks down, SQL breaks down. And you have to start reaching for graph-oriented tools. And that's all I have.